In this video, we're going to use the node voltage method to find the current I/O, which is the current flowing through this 6-volt source. Now the first thing we're going to do is we're going to identify all of our essential nodes, and we're going to choose one of those essential nodes to be our reference node. Now I know this is an essential node right here, and I'm going to choose this node to be our reference node. Usually we choose the bottom node to be the reference node. Now I know we're going to have an essential node right here. I'm going to label this node 1. We have another essential node right here. I'm going to label this node 2. And we have one more essential node. I'm going to label this node 3. And we're going to be using the node voltage method, which means we want the voltage at each node. So I'm going to write V next to node 1. This stands for the voltage at node 1. I'm going to write V at node 2 and V at node 3. Okay? So we're going to be using the node voltage method to find for the current I/O. Now the first thing we're going to do is we're going to write down a node voltage equation for node 1. When we look at node 1, right, we know we can assume the current is leaving this node, right? But when we look at this, we have a situation where one of the branches has a single voltage source. So this branch right here has a single voltage source. So because this branch has a single voltage source, we know the value of that voltage source is going to be the value of the voltage at node 1. And due to the polarity of this voltage source, we know this is going to be a positive voltage. So we don't even have to write a node voltage equation due to this voltage source right here. Therefore, we can say V1 equals positive 12 volts. Now let's look at the voltage at node 2. Well, we know this is node 2. So we're going to assume the current is leaving this node, right? So the current is going to go this way, and this way, right? That's what we're going to assume. When we start to write this out now, we can say node voltage at node 2. We're going to have V2 minus V1 divided by 2000, right? So we have V2 minus V1 divided by 2000. Plus, we have V2 over 1000, right? Plus, we have the current going in this way. But wait a minute. When you look at this now, we have a voltage source between two nodes. That's very interesting, right? Usually, when you have something like this, you're going to apply a concept known as the supernode. But the supernode is only going to be applied when you have a voltage source between two unknown nodes. Let's look at this for a second. When we look at node 3, we know the voltage in node 3 because node 3 is very similar to node 1. We have a voltage source in one of the branches by itself, which means the value of this voltage source is going to be the value at node 3. Now, because of the polarity of this voltage source is actually going to be a negative voltage. So we can say V3 equals negative 6 volts. So we have the voltage at node 1. We have the voltage at node 2. So when we look at this now, we don't even have to use the node voltage equation anymore to find the voltage at node 2. Now, because we can't do the supernode method, we have to rethink this, right? So I know I started to write the node voltage equation for node 2, but we know what node 3 is going to be. We know node 3 is negative 6 volts. So to find the voltage at node 2, we have two options, right? We can either, let me just cross this out. Because of this voltage source, we cannot go this route here anymore, right? And because we know the voltage at node 3, we cannot do the supernode method. So what we could do is we can say the voltage at node 2 is going to equal, well, when you look this way, there is no resistor, right? So we have 4 volts, and that's going to be a positive 4 volts minus 6. So when you solve for this, V2 must equal negative 2 volts. So we know the voltage V2 is going to be negative 2 volts. Now, if you're having trouble seeing it that way, now you can use KVL to find the voltage at this 1K resistor, once you find the voltage at this 1K resistor, you know that's going to be the same voltage in node 2. So let's do that to make sure we get negative 2 volts. So we're going to say KVL, I'm going to do it right here, KVL at loop 1, right? We're going to assume the current is flowing in a clockwise direction. So we're going to label the polarity as positive to negative, because current is always going to flow in the positive direction in a resistor. So we're going to enter the positive terminal, and because we want to find the voltage, let's just add in a current. So we're going to assume there's a current flowing this way, and we're going to label that current I1, right? So we have I1 flowing into this resistor as we walk around. So that's going to be 1000 I1 for the voltage across this resistor. As we continue to walk around, we're going to enter this positive 4 volt source. So because we're going to enter the positive terminal, we're going to have plus 4. Then as we continue to walk around, we're going to enter the negative terminal here. So we're going to have minus 6 equals 0. Now when we start to solve for this, we're going to get 1000 I1 equals positive 2. Therefore, I1 equals 2 milliamps. So we found the current flowing through this resistor. Therefore, to find the voltage at this resistor, we're just going to use Ohm's law. We know the current flowing through it, and that's going to be 2 milliamps multiplied by the value of that resistor, which is 1K. So we can say V2 equals 2 milliamps multiplied by 1 kilo ohm. When we solve for that, the voltage across that particular resistor is going to be 2 volts. But pay attention to the polarity. Do you see how the polarity is written? Which means this is not just 2 volts, but it's actually negative 2 volts because of the polarity, right? So because we know it's a negative 2 volts, we know we got the same answer as what we got when we first just added these voltages together, right? All right, so we know the voltage, we know the current flowing through this resistor. Now they want us to find the current IO, which is the current at the bottom node. So this current right here that's going to be flowing in this 6 volt source. There are 2 ways we can go about this. So we can either do KCL at this node here to find the current I0 that's going to be leaving this node, or we can do KCL here and find the current IO that's going to be entering this node. Any way you decide to do it, you're going to get the correct answer. Now the way I'm going to do it is I'm just going to find the current that's going to be entering this node here, right? Now what I'm going to do is I'm just going to find the current that's going to be in this resistor here and in this resistor here. So let's do that, right? I know to find the current in this resistor here, I can just use Ohm's law, right? So I'm going to treat this. I'm going to assume the voltage polarity is going to be positive to negative, and I want the current that's going to be leaving this node. So I'm assuming that we have a current that's going to be leaving this node and going in this direction here. So it's going to enter the positive terminal first. I'm going to call that current I2, and to find the voltage, all I'm going to do is I'm going to take the difference in voltages between V1 and V2 and divide by 2000. So we can say I2 equals V1 minus V2 divided by the resistor, which is a 2K resistor, so 2000. V1 we found to be 12 volts, so we can say I2 equals 12 minus V2, which is negative 2. So we got negative 2 volts, right? All of this divided by 2000. So when we solve for this now, I2, which is the current flowing to that resistor, is going to be 12 plus 2 over 2000, which is going to be 14 over 2000. Therefore, we can say I2 equals 7 milliamps. So we know there's going to be a 7 milliamp current flowing through this resistor here. So we know I2 is 7 milliamps. We know the current I1, we know the current I2. So it's very easy for us right now, instead of finding the current through this resistor, to actually find the current flowing through this 4-volt source, right? We're going to assume that the current is going to go this way. So we have this current coming in, this current coming in, and they're going to leave to go in this direction here, right? So to find the current going in this direction here, we know all we have to do is we're going to use KCL at node 2. So we can write this as KCL at node 2. The current entering this node is going to be the current I1 and I2. So we have I1 plus I2. And we know we're going to have a current leaving. We're going to call this I3. So current I3 is going to be leaving this node. So that equals I3. We know the current I1 is 2 milliamps. So we have 2 milliamps plus the current I2, which is 7 milliamps. So we have 2 plus 7. And all of that equals I3. Therefore, we can say the current I3 equals 9 milliamps. Right? So this is not our answer, but we know the current flowing through this resistor. Now remember, they want us to find this current here. Right? The current entering node 3. So to find that current I3, we can just do KCL at node 3, right? But to do KCL at node 3, we're going to have to know the current through this 1K resistor. So we're going to assume that the current is going to flow in this direction. So we're going to have a positive to negative terminal. So to find the current, I'm going to label this current I sub 4. To find I sub 4, we know we can just use Ohm's law. We can say V1 minus V3 divided by 1000. So let me just circle all of the currents that we know so far, right? We know this current, I1. We know the current I2. We know the current I3. So now let's find the current I4. So to find the current I4, we're going to have I4 equals V1 minus V3 divided by the resistor, which is 1000. We know V1 is going to be 12 and V3 is negative 6. So we're going to have I4 equals 12 minus negative 6 over 1000. So when we solve for this, the current I4 equals 12 plus 6 over 1000. Therefore, I4 equals 18 milliamps, right? So this is the current I4. Okay, so now that we know the current flowing in this resistor, we know the current flowing to this voltage source. To find the current I0, which is the current flowing through this 6-volt source into this node, we can just use KCL, right? And because we have all of the currents flowing in this node, we're going to add I0 plus I3 plus I4 and set it equal to 0. So we're going to do KCL at node 3. So we're going to have I0 flowing into that node, plus we have I3 flowing into the node as well, plus I4 that's going to flow into this node. And all of that must equal 0. Now we know they want us to find I0, but we know I3. We know I3 is 9 milliamps. So we have I0 plus 9 milliamps plus the current I4 we just found was 18 milliamps. So we have 18 milliamps, and all of that equals 0. Therefore, I0 equals negative 27 milliamps. So this is going to be our answer for this particular problem. the current I0 equals negative 27 milliamps. So this problem was definitely more a test-like problem. We didn't really have to write the node voltage equations, because once we started to write the node voltage equations, we identified that we had voltage sources that were in the branch, and they were in the branch by itself, which means that we knew the voltage at those nodes. We knew the voltage in node 1 due to this voltage source. We knew the voltage in node 3 due to this voltage source. We were able to find the voltage at node 2, and once we knew the voltages at each node, we were able to find the currents in each branch of this circuit. But we had to use KCL and Ohm's law a lot in this particular problem. That's why I always say we have to be comfortable with the tools we have in our tool bag already, because they're always going to come back and we always need to pull them out and know what we're going to do when it's time to solve these problems. I remember when I first started to solve these problems, I would get so confused. But then you have to ask yourself, could we use KVL here? Could we use KCL here? Could we use series parallel resistance here? And because I asked myself those questions, I was able to know we have to use KCL, because they wanted us to find the current, and the only way to find the current in this source right here without a resistor is to use KCL at a node. So this is it for this video. This was a great question.